Welcome everyone to this talk on the history of paleogeography and exploration, lessons from the past for the next generation of explorers. My name is Paul Markwick. I'm CEO of a company called Knowing Earth, as well as visiting lecturer at the University of Leeds and a visiting research fellow at the University of Bristol. This talk was originally presented at AAPG in San Antonio back in 2019, with a version published in AAPG Explorer magazine in August 2020. My thanks to Matt Silverman and Amanda Haddad, who co-chaired the session in which I presented this talk. This was on the Sunday of the meeting and titled Step Changes in Petroleum Geology, Historical Challenges and Technological Breakthroughs. The history of science is so important if we are to understand the background to the concepts and ideas we use on a daily basis. And I certainly encourage everyone who attends AAPG, at least once we get past the current lockdowns, to attend the history session. You'll find these very interesting. As well as history, we as geologists appear to be drawn to coloured pencil crayons, drawing maps and drawing field sketches. And if we have seismic on a printed piece of paper, well, what more could any geologist want? Forget about AI and big data. Pencil crayons rule the day. But why? Well, partly it's because geology and the earth sciences are so visual. Now that is something of a cliche, but no less true. But I would suggest it's also because our science is so diverse, with so much information that we need to find ways to clarify and simplify our problem solving. And colouring and large pieces of paper are a great, dare I say, low cost way of doing this. Now, a little bit of background about myself, which may explain my interest here and some of the things I'm going to show you. Now, I spent the initial 2 years of my career at BP in Sunbury-on-Thames before moving to Chicago, where I studied with Professor Fred Ziegler's Paleogeographic Atlas project. Some of you may know about that or remember some of the maps that were done back in the 1980s. This was followed by a postdoc at the University of Reading, researching the exploration significance of the paleoclimatic and drainage evolution of southern Africa using computer-based climate models. This was with Professor Paul Valdez, who's now at the University of Bristol. After that, I went to Robertson Research, which is of course now part of CGG, as a staff petroleum geologist, where I worked on a number of projects and helped develop the global predictive models of source and reservoir facies that some of you will have used. This is now called Merlin, or at least it was called Merlin. I think it's now called CGG Predictions. In 2004, I moved to GTEC to set up the Petroleum Systems Evaluation Group with John Jakes. And from 2006 to 2017, I served on the GTEC board, overseeing the sort of strategic technical direction and much of the technical developments we did. We saw the business transition and grow from an academic research group to a multi-million-pound company with 4 offices, 120 staff and an international client base. Now, my research interests are quite diverse. Everything from global tectonics to paleogeography to paleoclimatology, the history of geology and depositional modelling. And this might explain some of the things I'm going to talk about today. One of the problems, as I said right at the beginning, is that in geology we have so much to take in. And this applies to solving exploration problems as much as it does to here teaching field geology to the MSc course at the University of Leeds. Now, many of you, I'm sure, will recognise this view as we look down from the castle of Saint-Mentier, which is just coming into the picture now, north towards the Ainsa area and the deepwater turbidites of Emiliano Muti. That's at the head of the reservoir, and in the far distance the snow-capped mountains of the axial zone of the Central Pyrenees. And the fundamental problem here is, where do we start? And as I said, that applies to solving an exploration problem as it does to teaching. Do we just focus on the structural evolution? And certainly for the MSc, that's what's written on the tin, if you like. We've got the Mediano anticline here dipping away to the north, the complexity as we look into the Cortilla thrust in the middle ground And this area here as part of what Munez calls the Ainzer oblique deformational zone. Very, very interesting, very complex. And certainly we could spend all our time just looking at structure. But the area is famous for the deep water turbidites. So should we spend some time looking at the reservoirs, the Ainzer turbidites? Well, actually we do. And we have our good friends from Shell come along and spend a day with us talking about the turbidites, and then we integrate that in with the structural evolution. Do we focus on the depositional systems, maybe not just the turbidites, but the fluvial systems, the deltaic systems, the carbonates, or the source to sink story, or the climate? Well, quite a lot of complexity there. In reality, of course, we have to look at all of those components. And therein is a problem. How can we do this without losing our audience or spending so much time on a problem that all sense of commerciality is lost, as it would be in exploration? Turns out this is not a new problem. 200 years ago, the early geologists were faced with exactly the same problem. As observations expanded the knowledge and databases of the time, the world's libraries and museums, and geologists were trying to grapple with that vast volume of information. One of the solutions the early geologists came up with was paleogeography, a way to provide the context for showing all of their data. Now, initially these were just land sea maps, and this particular example here is from Charles Lyell's land sea map of Northwest Europe. This is from his 1837 edition of the Principles. And the darker colours here, the darker shading and marine conditions, and then we're looking at whether it's terrestrial deposits in the sort of bluish colours, or whether we're looking at uplifted areas. Now, this sort of work was being done by a number of people. Elie de Beaumont in Paris was doing a very similar thing, although unfortunately I've never been able to get hold of some of his maps. So certainly if any of you can point me in the direction of those maps, I would be very grateful. But it was to be one of the first petroleum geologists who really saw the value of paleogeography, especially in resource exploration. This was Thomas Sterry Hunt, and he was important for a number of reasons. First, he gave us the term paleogeography. Secondly, he was a petroleum geologist, so he was thinking about how you apply geological understanding to actually finding resources, in this case oil. He also recognised that you can use paleogeography to bring all of the components together, all of the different aspects, the climate, the land-sea distributions, the rivers, etc. And finally, he also recognised that to build a paleogeography, you need to first to understand the crustal architecture, or the architecture of the Earth as he referred to it. Unfortunately, Hunt's work was not fully utilised. It's true that through the following 40 years there were a vast number of paleogeographic maps produced, from Jukes Brown's building of the British Isles in 1883, in which he showed some paleo-rivers, albeit their general pattern only, to Dana's work in the US. Indeed, by the end of the 19th century, we have the very first global paleogeographies, those of Lapointe in 1900, and you can see some of his volumes here on my shelf. But again, all of these were very much land-sea maps. Interestingly, the major developments at the turn of the century were in Germany, with the work of Cosmat, Arlet, and Arlet, of course, you can see his Handbuch of Paleogeography on the left-hand side of this picture, and of course ultimately then these workers leading on to Wegener's work in 1910s. It is one of the great tragedies of science that their work was largely forgotten or lost as a consequence of the politics of the early 20th century, and that is a real shame because there's so much information stored in it. Now, when I say lost, it wasn't actually fully lost. It was to be an American, another American, Charles Schuchert at Yale, who was to take paleogeography to the next step. Now, it turned out that Schuchert knew the work of Steary Hunt, and he took that workflow and added to it. But he also knew the German literature. Indeed, his parents were émigrés from Germany, and he was able to pull all of that together, much of which was largely ignored by the rest of the community, to start to build up the paleogeographies. He also stressed the need to do this in much more detail, both spatially and temporally. His argument was to ask, what was the point in drawing a, quote, Cretaceous paleogeography when the Cretaceous was millions of years long? It's something that people tend to forget even today. For Schuchert, the maps needed to represent as fine a time interval as was realistic with the stratigraphy of the day, and that really was the sort of formation level in the stratigraphic terminology. Now, Schuchert was a colleague of Joseph Borel, one of the founders of modern stratigraphy, and so it's not surprising to see this link between paleogeography and stratigraphy. And this led, in 1910, to Schuchert's Paleogeography of North America. And there's an image here on the right-hand side from the Turonian. This is actually a reprint from 1955 of those original maps. And the darker colours here representing, of course, the Western Interior Seaway is most of what we see. This atlas of Schuchert comprised about 60 maps at a much higher detail than had been done before, and very much set the tone for paleogeography throughout the 21st century, or sorry, the 20th century. Jumping ahead a little bit there. But Schuchert didn't stop there. He also recognised that we need to look at where the mountains are, where the rivers are, what the climate is, and how it affects the landscape. All the components that we think of today were described and discussed by Schuchert in his workflow, because, as he put it, to understand the Earth system, we need to understand how all of those components interact. And that requires paleogeography as a tool to bring everything together and see how the system works. Interestingly, it was Schuchert who said that to correctly map a collisional system, you need a palinspastic base map on which to do it. So that's deformable plates to you and me. It was also Schuchert in 1919 who promoted, again, as had Hunt 40-50 years before, the use of paleogeography in the petroleum industry. Unfortunately, just like Hunt, Schuchert's suggestion was not really taken up by the industry, such that by 1943 and another eminent petroleum geologist, John Emery Adams, was to lament that despite its clear applications in exploration, paleogeography was still underutilized in the industry. There were more maps, certainly, but no one was using it fully as a tool. Now, Adams gave three potential reasons. Firstly, paleogeographic maps are labour-intensive and take a long time to build. Secondly, we rarely have the temporal resolution needed, going back to Schuchert's concern. And thirdly, paleogeographic maps are never finished. Now, what he meant by this was that no sooner had you drawn a map, which had taken you a long time to do, than new data became available as these databases expanded, and you had to go back and change your map. Something that is incredibly frustrating, and certainly from my perspective, having tried to sell paleogeography over the last 30-40 years, telling people that they're never finished is not a good way of closing a deal. Now, Adams went further in suggesting that by using paleogeography together with climate, you might be able to predict source and reservoir facies. Part of what Adams included in what he called his lithogeological maps, which were very much sort of the precursors of the play concept. Now, I sort of said that the maps remained very much sort of land-sea maps. There were exceptions, and I'm indebted to James MacDonald for drawing my attention to this paper by Pepper et al. In 1954, in which the authors made an attempt to reconstruct the landscape and rivers for their time slices. This is actually from the Appalachian Basin, from the Devonian, and here we can see an attempt to put in the paleo river systems, the shoreline, and the mountains as well. So there were people thinking about this, thinking back to what Schuchert had said, thinking back to what Hunt had said, trying to pull all of this together. And then, in the late 60s, everything changed. And it changed because of plate tectonics. And this really kick-started the use of paleogeography in exploration. Once plate tectonics came in, then people started to put coastlines and land sea maps on the reconstructions. And if you could do that, then you could plot out your exploration data in its original paleo positions to understand how it formed and why, the depositional setting, the juxtaposition of different elements. And the result was an explosion in paleogeographic research, with companies either generating their own maps internally or working with research groups to do so. This growth proceeded for the next 50 years up to the present day, and we can think of the work of Smith and Dryden, Peter Ziegler's work out of Shell. This is from his Northwest Europe Atlas. We've got Durkheim's work here, and Torsvik and Cox. Really quite nice summary of Earth history and paleogeography, up to the present day with François Gilchaud's group at Rennes, and this is Chabarot's work in 2012. Slightly different approach, more sort of fascies, but some really, really nice maps. And of course the really beautifully photoshopped images of Ron Blakey, which we can see on many of the posters at AAPG and many other conferences. But to look at the implications for exploration, I want to go back to the 1980s and to Chicago and the work of Fred Ziegler's Paleogeographic Atlas project. And the reason is because of what Fred did, not just in terms of plate modelling, which his group did, and people like Anne Lottis and Dave Rowley, but how he mapped and what he mapped, and more especially how he dealt with big data and auditing that data in terms of data management. So here's a picture of the Heinz Laboratory in Chicago, which is the home of the Department of the Geophysical Sciences. It's a lovely picture, this I got from Sebastian's website here. There's a link at the bottom, and it really makes it look really, really nice. Actually working there, it is one of the most awful buildings in the world, but it won an award, which perhaps explains a lot. This department had an incredible diversity of expertise. And in one corner of the second floor was the Paleogeographic Atlas project of Fred Ziegler. And on the right-hand side here, we have a picture of Fred teaching students. This is actually out in the Appalachians, if I recall correctly. Mike Holver sitting in the middle there. And then a picture of a very wet Fred Ziegler doing fieldwork in China, a great trip that we all went on, doing some work there. Now, the Paleogeographic Atlas project spawned a whole series of experts and people that many of you will be familiar with. Chris Scotese, of course, was a postdoc here and has probably done as much as anyone to promote paleogeography over the last 40-50 years. Dave Rowley is still at Chicago, his work on plate modelling initially and more recently on mantle convection models and uplift and so forth. But the key developments in terms of Fred's work and his group's work back in the 70s and 80s can be summarised sort of here with four broad developments. Firstly, that Fred reconstructed paleolandscapes, the paleotopography and the paleobathymetry, and did that systematically. There was also the data management and the databasing. Recording uncertainty. How do we qualify the data? And then he also considered the broader Earth system, with research on plate tectonics, of course, but palinspastic restoration, paleobiogeography, paleoclimatology, and paleoceanography. Now, I've mentioned again about this change from land-sea maps to the importance of the work Fred did with paleolandscapes. The question is, why are paleolandscapes so important? Very simple, really. Because it's on the landscape that the rock record is built. A particle sees topography, rivers and oceans. It doesn't see or understand mantle convection or hyperextension, at least not directly, only through the landscape. Now, I use the term understand in the loosest possible way, of course. Now, how sediment is formed in the hinterland through weathering and erosion, transported and ultimately deposited, is a function of what happens at the surface. And the product of all of that, of course, is the rock record. And that's what we drill. So here's some examples. On the left-hand side, these are some of Fred's original maps. This is from his 1985 paper, which is a great paper, really seminal piece of work, which I encourage everyone to go and have a look at. At the top, we have the present day of North America, showing his divisions of topography, and then the database for the present day with the dominant lithologies shown for each grid cell. In this case, I think it was about a tenth of a degree. And below, the Cenomanian. And again, you can see that reconstruction of topography, but then the data superimposed on top that gives you that confidence of what the map's based on. On the right is some of my work, more recently, again following the same sort of methodologies. This is actually for the South Atlantic, specifically the West African margin. We've got the Bohemian here, and then the Maastrichtian on the right-hand side. But again, the ideas of building up from the data, the crustal architecture, up through into the topography. The big difference with this more recent work is the inclusion of a much more robust reconstruction of the river systems. Now, this landscape that we're reconstructing is a balance. It's a balance between tectonics, which is why we need to look at that, but then also the negative forces of erosion. And again, we need to start to look at all of those to understand how the landscape's behaving. So to get at all of this, we build up in a systematic way. And you can see here, this is sort of building up to an example. This is actually from the Red Sea work I was doing a few years ago, where we're again building the structural framework, the crustal type, geodynamics, all the way through depositional systems and paleodrainage. And by applying that systematic workflow, we can control the build at every stage. It also means we can control the confidence of each element that's going to build that landscape. We can then start to add more complexity. In this case, this is actually some of the work from Dave's work back in 2013 with his colleagues in Canada, looking at high-resolution mantle convection using some very, very powerful models. This is actually for the Pliocene, looking at the evolution of uplift due to short wavelength mantle effects, and then comparing that with shoreline positions. Really, really interesting work. So we can start to add that into the mix here, but we have to build this systematically. It was now really at this time in the 80s that explorationists realized the significance of paleogeography as a tool, especially when the maps were linked with Earth system models to retrodict the source fasces and then clastics, starting with the seminal work of Judy Paris, who was also a member of Fred's group at Chicago. And this is one of Judy's maps here in the Cretaceous, and you can see this sort of the pressure systems that she's drawn onto the paleogeography, picking out upwelling zones, which are those sort of hatched areas, and then plotting as well data points showing whether you've got source rocks or non-source rocks. Now, that work was actually taken by Chris Scotese and Colin Summerhays in 1986 and computerized, so the whole process was much quicker and more robust. And that became ultimately the parametric model that many of you would have seen in products used by various groups. Now, the difference here is these models are based on the pattern of climate. They are not full dynamic models, which is what GCMs or global circulation models are. This picture here shows the results from one of those GCMs. It's actually, this is for the late Cretaceous, the Maastrichtian. It's some work that I published on a few years back. The top picture shows particulate organic carbon retrodicted through a process-based model that took in not just upwelling, but also fluvial sources of nutrients, looking at storm-generated nutrient sources, but then also considered the transport of organic matter and then the preservation. And in the lower picture, with those greens and yellows, are grain size of clastics, and this is the potential distribution, assuming that the sediment of that grade is available, based again on Earth system models, in this case also including tide models. So we can do much more advanced modelling today, but some of the ideas, or much of the ideas behind this, go back to the early 80s, and indeed, of course, go back even further to Adams' suggestions back in the 1940s. Now, what Fred and his students discovered as they built their databases was the need to better know the data itself, especially its provenance and reliability. Just because we can access and compile huge databases does not mean that the data is good data. Now, the internet, as we all are aware, is powerful for good and bad, with fake news and alternative facts, so we need to be very careful about data. Put simply, big data is great, but big bad data is just bad. What Fred did was to find ways to qualify data quality and also confidence in mapping. Now, this image here shows a recent iteration of the simple confidence scheme that Fred adopted and actually was published in 1985. Now, I've brought versions of this to various companies I've worked with over the last 20 years, and one of its strengths is a very, very simple scheme. 0 representing, if you like, government health warning, 5 being, I've stood on the fault, I know it's there. Now, being simple means that it gets populated within the database, and that's critical. The whole idea here is about ensuring that we know the provenance and quality of data, and this can also be done through a more extensive data audit. At the bottom here, you see one of the attribute tables. This is from one of my own recent databases, and here we're recording things like explanation of why the feature was drawn, the mapping confidence following that scheme of Fred's, but then also things such as who was the compiler, what are the references, how good is the age dating, and so forth. And this means that anyone using this data can go back and say, I disagree with that. I understand what they've done, and I know why they've done that interpretation, but, for example, I have better data. It allows us then to understand the provenance of that data and to always go back. Now, we can also add additional information, and certainly in my own work, I use scrapbooks of key information. Now, today, they're not actually physical as shown in this picture here. They're actually all digital, of course. But the idea, and again, it goes back to Chicago and Fred's work, is that you're storing as much information as possible. You can always go back and check what you've done. And that's crucial. So let's go back to the paleogeography and let's see how this actually works. So in this case, we're going to go back with an example. For the Central Pyrenees, we're going to go back to that picture I showed right at the beginning, which is actually right bang in the centre of this background photograph at about 6.5 on this map. Now, this region here is shown in the insert. You can see the sort of region of the Central Pyrenees, and we're going to build a paleogeography for that. So the first thing is to get all of our structural data. Now, in exploration, of course, we'll have seismic. Here we do have some seismic, but we've also got the outcrops that we can build our structural model. And the key is to record, where possible, primary observations. Putting that together, the kinematic evolution, the timings, the stratigraphy. Again, in exploration, we'll have well data, and of course, we do here in Spain as well. And so we can plot out our structures, and then what I've done here is to also put on top the geodynamics. And the different patterns here, and it's a bit small, I know, in the key, these are all showing in purples the compressional systems, but the diagonal pattern and the different density of the diagonals shows when it was last active on this bit of the crust. And what you can see is actually throughout the whole Pyrenees, there is no evidence of compression at the present day. Now, this may explain why there's a very serious lack of seismicity. But if we look at this, this gives us a sense of the different thrust sheets. It gives us the geometry of how this area has behaved. So we have our structures, and what we want to do now is to pull out of this the information we're going to use for a paleogeography. Now, in case any of you are wondering, the different coloured dots there are localities that we take the MSc students to, and the colours represent different days. And again, if people have questions on that, please don't hesitate to contact me on that. So what we're going to do, we're going to select a time slice here in the early Eocene, And this particular stratigraphy is from Elizabeth Morris's PhD from 2013, a really, really nice piece of work. We're looking actually in that stratigraphy of going from east on the right-hand side to west on the left-hand side. So actually it mirrors exactly the extent of the map that I'm showing. And you'll notice that in doing that, selecting that time slice, I've selected features of that age. And you'll notice also the kinematics have changed on those. So we're now seeing a lot more red activity, which says they're active. We've still got black there as well, which are inactive features. But overall, we've only selected those features in their present day geometry that are appropriate for this early Eocene map that we're going to reconstruct. Now, here is the geodynamic picture in the early Eocene. So now what I've done is to reconstruct the geodynamics, and you'll notice that much of that is now solid. We've got active compression. That darker purple is sort of thick-skinned, the lighter purple is the thin-skinned, and the area to the sort of bottom left, which is this sort of light brown colour, is what we're calling anorogenic land, by which we mean there's no active deformation there. So this is, if you like, the basement or the craton at the time. Not quite that simple, but this is the area that's not involved in the geodynamics at this time. Now, I mentioned before that this is showing the present day geometry. And immediately we've got a problem, because in the early Eocene, some of these piggyback basins were not in that position. So we have to go and look at Joseph Munez's work in the area and reconstruct the palinspastic reconstruction. And what you're seeing here is that geodynamics now, we've moved back all of these localities, moved back the different geodynamic units, the big thrust sheets, into the position that they may have been back in the early Eocene, certainly relative to the axial zone. Now we can start to think about how that might have looked topographically. So what I've done here is I've just put a hill shading on to say, look, this is high, this is low, here's the fallen basin. And what we can now do is to put the depositional systems on. Now, this actually takes a lot of work, and I've just done it at the click of a button. And here you see the deeper parts of the fallen basin to the west in the Hacher Basin. You can see the deep water there with the silts and mudstones. As you come south, you see that carbonate bank there. As we go into the Ebro Basin, what becomes the Ebro Basin to the south, the yellow represents delta top. This is a unit called the Castor-Cent Formation. The green here is fluvial systems, and then the brown depositional systems are alluvial fans that are feeding into this system. So it's a very, very active area, but there's a few more things that we can pick out here. You'll notice, I don't know if people can see sort of locality 2.5, sort of the middle part of the right hand side of this figure, and there's that slither of purple. That is the uplift related to the Montsec thrust, which is active at this time. And the key thing here is we're now putting the geodynamics and the depositional system together, and we can see how they interact, and we can see how that uplift influences the river systems and therefore the depositional systems. Now, of course, we can then turn that into a topographic map, sort of things that Fred Ziegler was doing. Again, there's uncertainties in exactly what we mean by how high is high, but the relative proportions here are probably about right. And then we can start asking questions of it. So we can think about the source to sink story, for example, going from the Castor-Cent on the right hand side, out across the shoreline, down the slope into the canyons, and here we've got the turbidites of Aroe sitting in the central picture there, and then out into the deeper water and the distal turbidites at Broto at locality 8.2 on this map, shown by the waterfall here on the left hand side. And we can start to think about actually how does this all operate? How do we explain this? The Castor-Cent is very coarse grained, very poorly sorted. What's the explanation for that? And we can start to piece together all the different components on a map and ask questions of it. We can then start to bring in, of course, paleoclimate. This is from some of the work on the early Eocene climate model. This is actually focused here on North America, but it's a global model, so we can apply that here and start thinking about how the climate change during this period may have affected the depositional system and how that interacted with the uplift story. So from all of this, we now know where the sediment is coming from. We know the length and nature of the transport pathways. If we add the paleogeology, which we can now do, we then have a way of understanding what's been eroded, what the caliber of sediment might be. And we can also then start to think about all the other processes that affect production of sediment, transport, and of course then deposition. Why is that important? Because downstream is one of our main analogues for deep water turbidites. This is from Ainsa. Now, I have to put a caveat here and say that Ainsa actually sits a little bit higher in the stratigraphic column than the time slice I just showed, and there's a little bit of a change that goes in the sort of 2-3 million years between the two. But essentially, we're trying to put together all of the different components to explain this. And then once we understand this system, we can then take that as an analogue to many other parts of the world. Now, this is just one example, but it gives us an idea of how paleogeography allows us to bring all of this information together. So to conclude, paleogeography enables us to compile, manage, analyze and visualize diverse geological information within the context of past landscapes. It allows us to consider all the inputs, especially the underlying crustal architecture, and think back to the work of Hunt and Schuchert and Ziegler. It makes us think about the temporal resolution. Again, Schuchert, Adams, Kay, people like that. It provides the basis for managing and especially qualifying our data. And this was the work that Fred Ziegler was doing back in the 1980s with some of those early databases or computerized databases. Incredibly powerful, incredibly simple, and incredibly important. It has the potential to be a powerful tool in exploration when built systematically, and especially when then combined with the other components of the Earth system, such as climate. To sum, paleogeography can be far more than just a pretty picture. With that, thanks very much for listening. I hope you found that of interest. If you have any questions, please don't hesitate to email me. The details are here for my contact information, and I look forward to hearing from you. Thanks very much.